example. Okay. We won't probably get through all of it, but cookies smell really good. I'll have some breakfast later. I didn't. Okay, so I know there's not a lot of room for you to write. I figured you didn't really need a lot of lines next to these, so I consolidated into like smaller paper, right? So you probably should, you could cut that out and put it in your notebook, right? And then write the example under it, because there's not going to be enough room. Well, maybe on the back you might have enough. However you like to do your notes, you know I don't grade them, so. A 1996 report from the U.S. Consumer Product Safety Commission claimed that at least 90% of all American homes have at least one smoke detector. Okay, so when it talks about some kind of national organization or big company making a claim, that claim is our null hypothesis. Okay, so we're going to test to see what we believe is true about this. Let me get a white pen. Okay. A city's fire department has been running a public safety campaign about smoke detectors with posters, billboards, and ads on radio and TV and in the newspaper. The city wonders if the effort has raised the local level above the 90% national rate. Building inspectors visit 400 randomly selected homes. Find that 376 have a detector. Is this strong evidence that the local rate is higher than the national rate? Okay. A lot of notation going on here, okay? We're going to start by writing our null hypothesis, HO. Our null hypothesis, H naught, is that P is equal to 0.9 or 0.90, however you like to write it. Your null hypothesis always says equals a value. It is never anything but equals for the null hypothesis. Okay? It's the alternative that takes the same statement and says greater than, less than, or not equal to. Okay? What is the question asking us? Well, yes, that's our sample, but the question's asking it if it's above 90%, right? They're hoping that they have more than 90% of their residents, right? So the alternative hypothesis, we write H sub A, P is greater than 0.9. It's not greater than or equal to, because if it was equal to, that's our null, so we just put greater than, okay? These numbers should, always be the same. Okay, I never change these numbers. It's 0.9, 0.9. The only thing that's changing is the null hypothesis is equal. The alternative is either greater than, less than, or not equal to. Okay. Then we'll check our conditions. Well, what do we have? P hat is equal to 376 out of 400. So that means N is 400, right? 94%. So our conditions, 400 should be less than 10% of all homes in the city. That's probably pretty reasonable considering the fire department had enough money to run ads and billboards and posters and radio and TV commercials. That's a big fire department, right? They're really trying to make a big effort. So it's reasonable to say that's less than 10% of all homes in the city. Does it tell us the sample was random? 400 randomly selected homes. So sample was random. Okay. Now, we have to check NP based on the hypothesis. So if I think that 90% is true, how many homes do I expect to have a detector? So that's 400 times 0.9 has to be greater than or equal to 10. and 400 times 0.1 has to be greater than equal to 10. Make sure we use the hypothesize P, not our sample. No, it's not. Our sample is 0.94. Our hypothesis is 0.9. Because the national rate is 90%, and this city, the sample gave us 94%. Yes, we understand that 94% is bigger than 90%. But is that a significant enough difference to say that the whole city is higher than the national average? Because that's just a sample. Another sample could come by and give you 89%, right? So is that difference sampling variation? Or did we actually raise the rate in that city? Okay. So that's 360 and 40. Oops, I forgot my 0 on that. So since conditions are met, a normal model is appropriate. And now I will use a one proportion z-test. Yes?
So it's the same conditions as what we were doing
Yep.
last chapter, but at the end we just...
Say z-test. Same conditions. The conditions aren't actually going to change this unit at all. Okay? The difference is I can't say 376 because that was my sample. I want to know if this is true. We're operating under the assumption that this is the true P. Okay? Then my standard deviation. Okay, my standard deviation is the square root of P naught Q naught over N, which just means we're going to use our hypothesis for our standard deviation. Because until we know otherwise, we believe it's still 90%. So everything we're doing in a hypothesis test is based on the fact that we believe the null hypothesis is true until we get to the end of our process.
And if it's not true, you just do the whole process again with different numbers?
No, we'll just create an interval real quick because our conditions have already been checked. So we just have to create an interval and then say this is what we think it is. Okay? So to be continued tomorrow. Okay, so we are picking up where we left off yesterday. We checked our conditions and we talked about the standard deviation for our hypothesis P naught. Every calculation we do when we're doing a hypothesis test is under the assumption that the null hypothesis is the true proportion. And we're trying to prove otherwise. Okay? So I had a hypothesized value of 0.9. So when I calculate standard deviation, it's 0.9 times 0.1 divided by 400. I'm not going to use p hat for the standard deviation. That's where things get confusing between the confidence interval and the test. Okay? The test, I use the hypothesis. The interval, I use my sample. It's the only p I have. Okay? So this square root of 0.9 times 0.1 divided by 400 is the standard deviation for our normal model here. And this is 0.015. And one of the steps is to draw the normal model so we kind of understand and can relate right now what we did in chapter 6 to what we're doing now, what we did last chapter to what we're doing now. So we're going to draw our model. Our mean is P naught, the hypothesis. Okay. And then my standard deviation is 0.915, 0.93, 0.945, 0.885, 0.87, 0.855. Okay, now we're going to draw on here our p hat, which was 0.9 what? Let's go back up. 0.94 was our p hat. So 0.94 is about here. So we're going to find the probability of getting a sample proportion as extreme as 0.94 or more extreme. Okay, we're finding the probability of getting a sample greater than or equal to 0.94. That's what we did in chapter 6. That's what we did last chapter, or chapter 17. Okay, we're finding the probability of this sample happening, given the null hypothesis is true. So what is that calculation if I want to find that probability? It is something we've done before. As well, it's not the z-interval. This whole thing is called the z-test. So I need to find a z-score, right? It's a z-test. We're going to find a z-score. So the z-score calculation is, remember, sample minus mean over standard deviation, right? Our sample is p hat. Our mean is p naught, the hypothesis, and our standard deviation of p naught, which is 0.94 minus 0.9 over 0.015. What was the sample minus the hypothesized proportion divided by the standard deviation that we calculated with the hypothesized proportion? 0.04 divided by 0.015. We get the z-score is 2.667. And then how do I find the probability for that? Normal CDF. Nothing new here, right? And which way is it going to go? Right, to the right, right? That's why we're drawing it and coloring it, because we can see which way we're going to do our normal CDF calculation. And our hypothesis, our alternative hypothesis, tells us which way we're going to go with that, greater than. So our z-score, 99. You'll look at your hypothesis, your alternative hypothesis. So if that's greater than, you're going to do 99. If it's less than, you're going to do -99. Yes, and then if it's not equal to, we'll talk about that next. So I got 0.00383. Okay, this is called your p-value. And we kind of started writing this sentence. This is how we're going to interpret our p-value. There is a 0.00383 chance of obtaining a sample as extreme. Why can't I spell right now? Or more extreme. That's because it's greater than, right? We're not just finding the one value. We're finding the probability of being greater than 94%. So it's that extreme value or more extreme.
I found this on the web.
Thanks, Siri. You're very helpful right now.
Using p-values in hypothesis tests. Okay. Siri threw me off. Then 94% homes with smoke detectors if the true proportion, maybe of homes with smoke detectors, that sounds a little better. The true proportion is 90%. Okay. We calculated the probability of getting a sample of 94% given the population proportion is the 90% that they claim it is. So our p-value means it's the probability of getting that sample if the hypothesis is true. And if that probability is low enough, do we really believe that that's the proportion in our city? Did you really believe that there was 50% red cards in that deck once we got to 8 cards in a row black? No, because the probability was too low for you to believe me, right? So what did you do? You called my bluff. You rejected the hypothesis. Okay? So we are going to reject this hypothesis because my probability is low. Okay? So we...
What else would, like, so we were continuing, like, what would be considered low?
Somewhere between... So low is usually below 10%. 5% is really low. So it's like below 5% for a p-value, 0.05. You're definitely going to reject that hypothesis unless they give you another value. And we'll talk about that value next Friday when we get to the next chapter. Because the next chapter is kind of like adding on a little bit of more conceptual ideas as we continue to work through these problems. So that value of 0.05 is usually the standard. If it's below that, we're definitely rejecting. If it's between 0.05 and 0.1, that's kind of a judgment call. Is 7% low enough for us to reject? Possibly. So we still think that's low, then we can reject. It's in that area where you could go either way and still get the problem correct. Okay? When we get to the next chapter, we're going to talk about what's called an alpha level, which is a standard we're going to set at the beginning of the problem. If it's lower than that, we're going to reject. If it's above it, we're not. And then we don't have to do any decision making. Okay? But we need to get into this idea of understanding that the probability is what we're finding. The probability of getting our sample if the hypothesis is true. And interpreting that p-value correctly, and then stating our conclusion correctly. So one of the things they look for in your conclusion is you have to link your p-value to your decision. Okay? So since my p-value of 0.00383, you must state the actual number in the conclusion. Don't just use the fact that you already referenced it, because sometimes you'll leave off the interpretation and only write your conclusion depending on what the problem is actually asking for. Is low, is so low. That's really low, right? It's below 1%. Definitely low enough for us to reject. I reject the null hypothesis. Because it's low, I am rejecting the null hypothesis. There is enough evidence to convince me the true proportion of homes in this city, homes with smoke detectors is not 90%. There's enough evidence to convince me that it's not my null hypothesis. Lots of double negatives in statistics. Don't take your double negatives out of statistics because your English teachers don't like them. Okay? It doesn't work that way in statistics. Okay? We aren't convinced that it's greater than. We just know that it's not, and this is what we think it is. We're going to create an interval to say what we think it is. But we could be wrong. This could just be a sample that got unusually high for no reason. So we never say absolutely we believe anything. Okay? So now we're going to create our interval. You might start writing more in my class than you do in your English classes at this point. Most of my students complain about that. Okay? Good news is I don't have to check conditions again. Okay?
You do this every time for like homework?
Uh-huh. Yes. The whole process. 2 or 3? Probably 3. Right? I mean, you generally don't have more than 5 questions usually anyways, right? So,
That includes more similar questions having 7 parts. Or 8 would be your 8 and 10.
yeah, I feel like the computer sometimes makes the problems longer than the book does. With 20 parts.
Where it had 20 parts.
Right, because each question, like in the book it said, answer this, 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 and this. There's like 5 things in the thing you had to answer about each question, and so it made all those parts. Okay, we don't have to check conditions for this interval. We already checked the conditions for the hypothesis test, and they apply to our interval. So all we have to do is the calculation. 0.94 plus or minus 1.96 square root of 0.94. I'm not going to teach you the calculator shortcut till after the quiz. 0.06. So on Friday, I will teach you. At this point, we'll use our calculator shortcut. Okay? But it's not like that much more work. Okay? Because I don't have to check any conditions again. I just have to redo the interval real quick. Right? So 0.94. Notice I'm recalculating my standard deviation. Because now we rejected that hypothesis. I don't think it's 90%. So I'm going to use my sample to say what I think the true proportion is based on my sample. Right? So you're saying, no, Miss Wheelock, there's no way that deck of cards is fair. There's no way it's 50%. Based on my sample, this is what I think it is. There's 0 red in there. Right? So 0.94 plus or minus. Oops, I don't really know what's going on here. Hold on. 1.96 times the square root of 0.94 times 0.06 divided by 400. My margin of error is 0.0233. So 0.94 plus 0.0233 is 0.9633. And minus that is 0.9167. So then I am 95% confident. The true proportion, why can't I write today? Of homes in this city with smoke detectors is between 91.7% and 96.3%. And you can write that as a percent or a decimal, it doesn't matter. So we've gone all the way through. We've said, okay, let's test the hypothesis that it's 90%. We think that city ran all these ads, right? They want to know if they were able to increase the number of homes that have a smoke detector above that 90% level. So they did a sample, and they compared the sample. Obviously, 94% is above 90, but is that difference sampling variation, or is it really because the proportion increased? And we believe it did increase. We rejected the null hypothesis, and we believe it's somewhere in between these two values. Landon.
If we fail to reject the null hypothesis, do we still have to create our assumptions?
Very good question. No. If you fail to reject the null hypothesis, you have no reason to believe that that hypothesis is not true, and so that's what you believe, and you do not have to create an interval. Okay, so only when we reject do we create an interval. And this is what happens in like if you're actually doing something like this for a company, statistically, you want to create that interval to say, okay, this is what I think it actually is now. We did a good job, right? On the AP exam, when you reject, you don't have to create the interval unless it asks you for it, because it's that whole double jeopardy idea. If you made a mistake and you failed to reject but didn't create the interval, you'd lose a lot of points, right? So they don't require that at the end of the problems just because they don't want to knock you off for not making the interval if you rejected. So, or if you made a mistake and failed to reject, okay? But for the homework, right, it's good practice, it's good statistics to say. There is no homework tonight. The homework is due tomorrow night on chapter 19. It's online, so it's more conceptual problems, right, as we work through and start doing some more of these. Tonight there is a sample, the practice problems that you can do to study if you'd like to. The quiz tomorrow is just on one confidence interval. You have to go through the whole process of the confidence interval. And I put that all in the Canvas thing. Check your conditions, right?
Last quiz.
Create the interval.